How's the homework coming?
I need help on one problem.
Okay, Casey, what problem do you need help with?
I'm pulling it up with, but I'm pretty sure it's number 7.
Suppose a 1.3 kilometer main span of steel. That one?
I don't know which equation that is.
Okay, so 1.3 kilometers and temperature change of 20 degrees, right?
Right. Is it the same equation as number 6 or is it
I forgot to mention, yes, I don't see Brandon or Eric. Right. Okay, so we have that's the information that's given us in its entirety. It says to show how much it's going to expand, and it gives you the number. So as we saw with the demonstrations, I put them away, but when I put my little things in the fire, they expanded. And the equation for that expansion, which you're right, I probably didn't do in class because I ran short on time, is the change in length is equal to the original length times a coefficient of thermal expansion multiplied by the change in temperature. So we were given the original length, 1.3 kilometers, and we were given the change in temperature of 20 degrees Celsius. But we have to look up that coefficient of thermal expansion for the material. The material here was steel. So alpha for steel equals, and I don't have my textbook with me.
It's 11.
Go ahead. Just
11 times 10 to the negative 6.
per degree Celsius. Actually, it should be per Celsius degree because a change in temperature is Celsius degrees. A temperature is degrees Celsius. That's a subtle point that I am never going to hold you to. So if we multiply these through, we're just going to have 1.3 times, what's a kilometer? What does it mean to be, what's kilo mean? 1,000. So a kilometer is 10 to the third meters, then times 11 times 10 to the minus 6 per, there I'll use it, per Celsius degree, and then times 20 Celsius degrees, right? That should have been over there. That should have been over there. And that gives us our answer. So you just pop it in the old calculator to get the number.
But you can't do that on like the phone calculator, right? The 10 to the 3.
Okay, on any calculator, on your phone calculator, if you turn it sideways, you get more options. And on any calculator, you should enter this in as 1.3 E3 times 1 E, that little, usually it looks like that minus sign, 6 times 20. You should always put this form for putting in times 10 raised to in your calculator, because then it knows that's part of the number. If you put multiplication, it means the same as times 10 raised to the third, but if you do it that way, it views it not as part of the number, but a new number you're multiplying by. And if you have a really, really bad calculator, you can use your head plus the calculator to get your answer. Because we have 10 to the third multiplied by 10 to the minus 6. What's 10 to the third times 10 to the minus 6? 10 to the minus 3.
Yeah.
And so I could say it's 1.3 multiplied by 11 multiplied by 20, and then the whole thing is times 10 to the minus 3. Right, so I can keep that times 10 to the minus 3 in my head, if I want. And notice the units, the per Celsius degree and the Celsius degrees cancel, so it's in meters.
And was that equation in the book? I just didn't see it.
Yes, in fact, it was in the heading for that section of problems. That I know I give you all the questions, but it is useful to look in the textbook because it usually has context for the block of questions that helps you out.
It's just at the bottom of the page of the previous page.
Jocelyn.
Can you explain what each of those things mean in the equation?
Each of the glyphs.
Yeah.
Yeah. Remember the first day of class I mentioned we have these symbols, and to me, they have great meaning. And to you, I know they don't initially. We have to develop that meaning. And so I have to remind myself that you don't always know. So what's the name of this letter? Okay, the name is delta and it means change in. So when I put delta L, that means the change in length. Now, what is the subscript 0 for the next one here? What does that mean?
Initial.
That means initial. So the change in length is equal to the initial length, right? So we can convert these symbols into words. Then we have this. That's, oh, excellent job.
Is that a constant like that?
Yeah, it's a constant per material.
Oh,
So we had to look it up for steel, and if it's steel, it's going to have that value.
so for
If it's copper, it's going to be a different value. So you'd have to look it up for copper if it was a copper bridge, which nobody makes. Okay, so that's supposed to be the Greek letter alpha. I actually drew it more like a proportional sign. It should be, more vertical on the end part than I tend to make it. So that's an alpha, and that's a constant. I can't give any special meaning to that. It's called the coefficient of thermal expansion. So it's telling you how much it expands when you heat it. And then the last one we have again delta, change in T temperature. So that's how to read it. Okay, is there perchance one more homework question? Brittany is raising 6 fingers, right? Brittany Renee Simmons, right? Since I called you Renee by accident last class period. Got to double down on it. Okay. Consider a 6.0 gram steel nail, 8 centimeters long, and a hammer that exerts an average force of 600 newtons on the nail when it is being driven into a piece of wood. The nail becomes warmer. Show that the increase in the nail's temperature is 17.8 degrees. Assume that the specific heat capacity of steel is 450 joules per kilogram degrees Celsius. Okay, I'm glad you asked me this one. Oh my goodness. It just looks cold out there. Had a little twisty action. I'm sorry. I love snow. Growing up by the beach, it didn't happen. Okay, so we have these important numbers: 6 grams, 8 centimeters, 600 newtons, 450 joules per kilogram degrees Celsius. Let's see if we can remember all of those. I'm just going to go to the bottom of the next page to work this one out. So we have a nail. Eight centimeters long. Mass is equal to 6 grams. Did I get those numbers straight? Not reversed?
Yeah.
Okay. And we have additional information. Force of the hammer is 600 newtons. And it says, assume the specific heat of iron is 450 joules per kilogram. It should be, again, Celsius degrees because it's a change in temperature. You'll see, everybody puts degrees Celsius, not Celsius degrees. And then we have to solve it. Who came to my office to ask me this question? Was it you? Or after class, okay. I was like, I know I did this. Okay, so thinking about this being a physics problem, physics is about thinking about these things and figuring out what's going on. You hit the nail with the hammer, and the nail moves. You put a force on the nail, it moved. What do we call it if you put a force on something and it moves? You did work to it. So the hammer's going to do work to the nail, so energy goes into that nail. Where does the energy end up? It ends up heating the nail. Now, how does that happen? You hit it, and it ends up getting hotter. Well, it happens because when it pushed into that wood, you have the friction between the wood. There's some other things that this is glossing over. You're compressing the wood. That's actually going to be heating the wood more than it's heating the nail. But we're pretending here that all of the heat is going into the nail. I said pretending. It's not all going to go into the nail. Some of it's going to go into the wood. So basically, our idea here is that work done by the hammer goes into heating the nail. So if heat goes into the nail, what should naturally happen to it? Okay, it is going to expand. Its expansion is going to be small. The more noticeable thing is it's going to change in temperature. It's going to have a change in temperature. So this heat of going into the nail is going to make it change temperature. And so we had an equation. The heat is equal to the mass of the object multiplied by the specific heat multiplied by the change in temperature. This equation looks almost exactly like the previous one, only the names have been changed. This here is now the heat. This is, of course, mass of the object. C is what we call the specific heat. If you want to be real technical, it's the specific heat capacity. And what that means is it's the heat divided by mass times change in temperature. And that's going to be different for each different type of material. So we have to know the specific heat of the material. Well, that was given to us. It was given to us right there. And then finally, we have the change in temperature. So I just put my values in. Actually, before I put values in, I'm solving for change in temperature, right? So if I want to solve for change in temperature, I have to divide both sides by MC. So the heat, I said the work done by the hammer goes into heating the nail. What's the equation for work?
Force over distance, or force times distance.
So that work is equal to the heat. So there I've written it out. So I have force times distance over mass times specific heat. Put in my numbers. 600 newtons times the distance. How far am I going to drive the nail? 8 centimeters. So that's 0.08 meters. Divide by the mass. What units does the mass have to be in? Kilograms. The problem gave us grams. So how do you convert it from kilograms to grams? Divide by 1,000, because you're dividing by a kilo, which is 1,000. So that's 0.006 kilograms. Sorry, my kilograms is not legible. And then finally, the specific heat of 450 joules per kilogram times Celsius degrees. And so when I look at this, a Newton times a meter, what do we call a Newton times a meter? Okay, it is a Newton meter, but also a joule. And so in terms of units, that's going to cancel. These two together will cancel with the joule. And then I have my kilograms canceling, and I'm left with 1 over degrees Celsius, which is degrees Celsius, or Celsius degrees in this case. And of course, 600 divided by 0.006 would be 100 times 1,000, so 100,000 times 0.08 would be 100. 8,000 divided by 450 is
17.8.
and it tells you what you're supposed to find. You said 17.8. So this was using equation. Remember, we talked about things like the specific heat of water. I know somebody put this as a question that was on our last quiz. Specific heat of water is the amount of heat required to raise 1 gram of water by 1 degree Celsius, and that, well, we call that a calorie. So it's 1 calorie specific heat of water. Any questions about the problem? Okay, Carmen, what's your other question? Number 10. Our class is a quarter over. Hooray. The source of heat of volcanoes and natural hot springs and trace amounts of radioactive minerals in common rock is, I'm sure I read that wrong, is trace amounts of radioactive minerals in common rock in Earth's interior. Why isn't the same kind of rock at Earth's surface warm to the touch? Now, to be a little more specific, obviously later on in this class, we're going to be getting into Earth science. And the Earth, over 99% of the Earth's energy budget comes from the sun. Right? Almost all of the energy we use ultimately can be traced to the sun. But volcanoes and hot springs are part of that remaining less than 1% that's not coming from the sun. It's coming from the interior of the Earth. And that interior of the Earth is because we have, well, basically uranium. Uranium is a radioactive rock. What it means to be radioactive is it's in an unstable configuration. Let's take an example of an unstable configuration. Okay, so here's 2 water bottles, and I put one on top of the other. It's kind of stable, but what happens as soon as somebody bumps it? It falls down. So it's kind of stable, but well, that's not enough, but that's enough. Boom, it falls down. Okay. So that's what basically is going on with the radioactive atom. The interior of the atom is in a situation like that where it was stacked up and it's kind of stable, but not really. So if it gets bumped right, it'll fall to a lower energy state. Those fell to lower elevations, lower energy. That's what happens in the nucleus as well. And when that fell, if you had, let's say instead of water balls, those were 10 kilogram masses, and you had your hand down here. When it hit your hand, it would have done work on your finger, and you would have known it, right? Well, it's the same thing. Energy is released, and it falls into a lower energy state. And that energy comes out, and it is what is heating up the Earth from the inside. So that's just to understand that beginning part of the problem. But now getting on to the real question. If we take that same uranium rock that is causing us to have molten magma coming out of the Earth, and we bring it up on the surface, we've got some rocks actually. There's some right on the other side of the wall there from where Jackie is. Most of them are up on the 3rd floor right now. Actually, we threw away the vast majority of our radioactive rocks. And you don't know there's anything to it. You pick it up, it doesn't feel warm. We don't worry about the safety, obviously, because it's very safe. Why is it not warm when I have that rock here and it's warm enough to heat and melt rock in the middle of the Earth? That's what the question is asking. So when we think about it, what has to happen for the temperature to go up?
Scarcity energy.
Okay, you have to have energy come into it for the temperature to go up. And so when we have that radioactive decay, that's going to put energy into it. But like if I went outside right now, my body is constantly generating energy, and yet I wouldn't feel hot outside. Why not?
Because it's going into the environment.
Because energy is going to go from me into the environment. Right? We have 3 ways of heating. 1 is conduction, direct contact. 2 is convection, that is some intermediary comes and takes it away, and that's what's going to primarily be happening outside. That intermediary is air. Air comes and touches my body. Heat flows from my warm body into the cold air. That air leaves and takes the heat away. That's what we call convection. And then there's radiation when something's giving off electromagnetic rays, which I'm going to start, when I start the lecture, I'm going to talk about that. If we have a rock on the surface of the Earth, can it lose energy through any of those three methods? Okay, it can have convection just like I would have if I walked outside. And so the air is going to be taking heat away, and if it's not producing the heat really quickly, it won't get very warm. If it's really quickly, it will still get warm. But if it's relatively slowly, it can take the heat away as fast as it's generating, it doesn't get hot. When it's in the center of the Earth, it's surrounded by a bunch of other rocks that are doing the same thing. So they're all giving off the energy, and they all just get warm together because they can't really get rid of it. You have conduction, but conduction takes time, and you don't have good conductors. You have reasonably good insulators in there, so you have very little conduction. There's very little pathway for energy to leave, and so it just gets hotter and hotter because the energy can't leave. So your key is, on the surface of the Earth, we have ways for the heat to leave, but when it's down buried in the Earth, it doesn't have ways for the heat to leave, and so the internal energy builds up and up, temperature goes up and up. Now for reals, we start the lecture. I'm actually going to, well, this here is continuing on with radiation. Something can be both heated by radiation and cooled by radiation. So let's take as an example, if it was a warm sunny day outside, or just a bright sunny day. Let's say it's a bright sunny day and it's 20 degrees out. If you have a skylight in your house and you stand in the light coming through the skylight, what do you feel? Warmth. Where did that come from? Came from the sun. That's radiation. That's electromagnetic rays that came from the sun. It was cold out there. We also don't touch the sun, so we're not having conduction. And none of our air reaches the sun, so we're not having convection. It's radiation that heated you up. And you can also emit radiation and cool down. So if you have something that's really hot, you bring your hand close to it, you feel that heat coming off of it, it left that object. So things can both heat and cool by radiation. Things that are good absorbers, well, just think about this. If you go out on a sunny day, what color of clothing is going to get the hottest and fastest? Dark colors. Black is the perfect color for absorbing or emitting radiation. It works both ways. If it's good at absorbing, it's good at emitting. So we actually call this black body radiation because black is the ideal color for it to work. Which is kind of funny because that means, you take an object and you put paint on it and you change how good it is at this process of radiation. So things that are good absorbers are good emitters. Things that are poor absorbers are poor emitters. So color is the first thing we point out. A white object is a very poor absorber or emitter. A black object is a very good absorber or emitter. Even better than those is something that is silvery reflective. Because if it's silvery reflective, what's it doing to all the light that hits it? Reflecting it. How much is absorbed if it reflects everything? None. So this is the perfect insulating color, making it perfectly reflective. So this is called a dewar. Most people think of this as a thermos. And its construction is designed to stop all three of the type of heat. All three of the types of heat. So first, what's the first type of heat we learned about? Conduction, direct contact. And so this has two walls. It has an inside and an outside wall. Each of these walls is thin. And so it has two walls that are separated by a vacuum. How will this vacuum, that is nothing, conduct heat? If there's no contact, you have no conduction. Because it's evacuated, you have no air flowing in there, so how much convection do you have? None. So it stops conduction and convection because you have no contact. Now you can say, and you're right, there is a path from the inside to the outside going along the glass. But the glass is thin. The thinner the glass, the poorer it is at conducting. And it's a long distance you have to travel. The larger the distance, the poorer the conduction. So it's designed to get very, very minimal conduction, no convection, and then it's coated with silver on the inside of the glass. What's that silver going to do? It's going to reflect radiation. So radiation that starts inside stays inside, that starts outside stays outside. Now, of course, it has a flaw, and that is because there's an opening here. And so you have to put a plug in here, and that's going to be your point of greatest weakness is that plug isn't as perfect as the rest of this. So this here is your practical example. It's the same device, but it's put in a container to keep it safe. Now, when I was a child, our thermoses and our little lunchbox we took to school were made like that. And as a child, what always happens? You drop it. And then you have all that glass breaks and you hear it shaking around. You're like, I broke another thermos. So they started making thermoses that aren't quite as good. Instead of using glass, they use plastic so they can drop them and you don't break them. I can't tell you, I probably broke like 4 thermoses as a kid because, well, I was a kid. No one should blame me. Anybody know what this is? Well, it's actually coated mylar.
Yeah, you did tell me that.
Mylar is plastic, so it's coated sheet of plastic. What's the purpose of this?
It looks like the balloons.
Mylar balloons are made out of the same stuff, yes.
Oh, to warm you.
It's to warm you up. You do something stupid like run a marathon, right? I mean, I think we can all agree that's stupid, right? No, it's putting undue wear and tear on your body. I don't care how fit you are. It's not good for you. Running, reasonably good, that not. So after you've exerted all that energy, you're low on energy. You're cold and you're having a hard time keeping your body warm. So they wrap you in this. When they wrap you in this, well, why is it colored silver? It's colored silver so it will reflect all the radiation coming off of your body back to you. And of course, the mylar doesn't allow air to go through. So when you wrap this around, you trap the air in. That's actually the bigger aspect of this, is just trapping the air in. Because air, if it's trapped, it's not going to convect anything away, not going to conduct anything away. And so the whole idea of this is to help you keep your body heat with you when your body can't warm you up enough. Now there is a second variation on this. When I was at PUC, I was on the ambulance and fire department there, volunteer. And we had to carry something like this in a little pocket on the side of our wildlife gear. And wildlands. And if there's a fire that comes roaring at us and we can't get out of its way, we take that thing and we had to practice, put your toes in it, flare it out, and then fall down backward essentially. Was that? Oh no, you put your heels, you go forward. You put your heels in, you hold it over your head and fall down forward. And you hold it like a little tent. And they teach us no one has ever died if they used it properly. Which properly translated means they just assume that if you died, you must not have done it properly. What would the goal of that little tent be? Yeah, because if the fire's coming so fast that you can't outrun it, it's going to pass you quickly. And so you pull that over you, and it's going to reflect the radiation coming from the fire. It's not going to allow hot air through it. As long as a burning ember doesn't land on you, you're probably going to be good. There's other things you do, like, try not to breathe, make sure you don't get any air from outside, because that air is going to be really hot and probably low on oxygen at the same time. You want to keep your oxygen in and your not hot air. But they use those for a safety thing because, well, we don't want our firefighters to die. Right? Okay. Just make sure you're with me on that. All right, so now we're halfway through the lecture, and we got our first clicker question. Which patio floor in direct sunlight? Now I want to make sure this is clear. All these floors are making good contact with the earth, and they're all getting direct sunlight from the sun. And unfortunately,
What's up?
I did not. I thought I had removed this. I will have to read this one for you. You see why I have a hard time reading what the numbers are? So this one here is a shiny, polished.
Another color. Maybe red and white.
You can read them on, you can read them on your phone.
Is that okay? It looks better on this. Okay, I can write it white. Yes, they can read it on their phone, but if they have a clicker, they can't. Sorry about that. I was supposed to remove this and those. Which one can you not read?
The dark B and F.
B and F. Okay, so this is
A polished steel sheet painted white and a polished hardwood floor painted black.
so just like the one below, but white. And this one here is just like the one above, but black. That didn't work out well, trying to color those two.
Wait, what's F? Black?
Which your question, Raquel? Okay, so we still don't have Jocelyn, Casey, Maggie, Hannah, Raquel.
I don't have my phone with me.
Okay. Tiffany?
Are you asking like highest temperature like to the touch or?
Highest temperature, not what's going to feel like when you touch it. I'm going to discuss all of this after we answer, but I'm asking highest temperature. So still, well, I will give it about 5 more seconds and then we'll go on. Okay. So our answers were change to color we can read 3, 0, 8, 1, 0, 2, 2. So let's start by, I'm just going to select people. I will start with Jackie and work over around like that. So Jackie, the first one, a shine, well, which one did you answer? And give us a reason why.
Okay. Well, I would say the polished steel sheet painted black
Okay.
because it's steel, and so I figured that it would absorb heat, and it's a darker color, so it'd be like a good absorber.
Okay, it's black, so it's a good absorber. And what difference does the steel make?
Just yeah.
Okay, good conductor. Okay, so she picked it because black makes it a good absorber and steel is a good conductor. What did you choose, Larissa?
I chose the same one.
Same one, okay.
Because it's good.
Skylar?
That's what I feel.
Okay, Tiffany? Brittany? Wow, we've got almost everybody with that answer already. Okay, so everybody in the front half answered. 1, 2, 3, 4, 5, 6. Two people in the front half answered differently. Carmen, what did you answer?
I answered A.
A?
Yeah, because since it's shiny and it's steel, like it's gonna reflect more, so I think in my mind it's gonna absorb more.
Okay, she said it's going to reflect more, so in her mind it's going to absorb more. What did you say? But C, okay. We got one more. What did you say, Dawson? Okay, we got all the C's out of the way. Yeah, what did you choose? I know you didn't have to have the clicker, but
I also chose
she would. See, that's okay because she didn't have a clicker. Raquel?
I chose G.
G, okay.
Because If it's, I just feel like the same amount of heat would be going to each of the objects. So even if like when you touch one, it feels hotter, they also have the same amount of heat because the sun is letting off the same amount of heat.
Okay, they all have the same amount of heat coming to them, is basically Raquel's. Okay, Maggie, how about you?
Actually,
D. Okay, shiny hardwood floor. Why shiny hardwood floor?
I feel like if it's a dark wood, then you can take in more sun and be hot.
Okay. Front row, Vanessa.
I chose F
Okay.
because I feel like the other ones would reflect the heat versus like absorbing it, and then the black. Because it's in the flavor, so.
Yeah, polished hardwood, floor painted black was one she chose. What about
I did F, but I'm second guessing myself.
you? You shouldn't, because that was the best answer.
Okay.
Was it? So
Yeah.
the answer's F.
So what did you answer?
But the answer's F though.
Well, yes, but I still want to hear reasons. Anybody? There are two people who said G. Just
Okay, I said A because I don't know. I was reading a book and there were two cups, pitchers, vases. Anyway,
yes, that is a sophisticated way of saying things. A box.
Anyway, so yeah, so there's like one that's black and the other one was like shiny. And they're like the shiny one is gonna have like be like more heat. So I feel like that's the answer. But the answer is F, so
Okay, well, there are things worth discussing here, right? This question wasn't a perfect clear cut. It's got to be this answer to anyone, right? You were all kind of putting ideas together. So, idea that we can all agree on. If it has more internal energy, it's going to be hotter. So more internal energy means that it's going to receive more heat and emit less heat. So let's start with receiving the most heat. How is the patio going to be heated up? Not likely convection if it's a sunny day.
Oh, radiation.
Radiation. If it wasn't a sunny day, then it probably would be convection. The example I used in class on Monday was in your house. And there likely was heated by convection. They were all heated the same. But here it's going to be radiation. And for radiation, the surface matters. What absorbs the best?
shiny. Metal.
Black.
Shiny metal.
I
Black.
thought you had said it. That's why you pointed
No,
to me.
I
I'm
was
sorry.
exact opposite.
Okay, so black absorbs the best. So the two black options are going to be receiving the most radiation. Now, as Maggie said, the hardwood floor, assuming it's dark, it's also going to receive a lot. So the hardwood that is shiny would also receive a lot, but probably not as much as the two black painted. Now, how are they going to lose radiation? Or excuse me, not lose radiation, lose heat. Okay, convection, you're going to have airflow over them. They're all going to lose heat through convection.
Like reflecting.
Reflecting is not losing it because you never had it.
Oh, true.
There's another way. They're all making good contact with the ground. They're all going to conduct heat into the ground. Now, convection and conduction, those don't matter what color it is. But conduction will matter how well heat conducts through the object. So which one would conduct heat better? The steel or the hardwood?
Steel.
Steel. So the steel is going to move heat to the bottom better, and then it can conduct away. So the steel is going to lose more heat than the hardwood will. So black is going to absorb more, steel is going to lose more. So the one that should be the hottest is the one that absorbs the most and loses the least, which then has to be the black hardwood floor. Now, before we start, Tiffany asked a question. She asked, does it like mean when you touch it, which one feels the hottest? And no, that wasn't the answer. Because which one feels the hottest is going to be the one that's giving heat back to you by conduction best.
Yeah, that's it.
And so like the hardwood floors, we said yesterday, if you touch it, it initially is hot, but then it's going to cool real quickly, and it doesn't feel like it's very hot. Whereas the steel, if the steel is hot, you touch it, it's going to stay hot, it's going to give you a lot. So if we were asking about which one's more likely to burn your feet when you walk on it, your answer would have to be the steel one that is the hottest. So the steel one that's absorbing the most would be, well, assuming the paint is thin enough that it's, it's anodized, so you don't have it acting as an insulator. But anodized is not actually paint. That would have made the black steel the hottest on your feet. Otherwise, probably the shiny polished steel, just because it's going to have the best conduction to your feet and still be hot. So there were a lot of things to think about here, which is why I put it in. I wasn't looking for people to get the right answer, but to think about the different ideas so that we can discuss them and understand them. And now I have 10 minutes left, and we haven't started electricity. These are just reiterating the points. I'm not going to spend any time on that. How quickly do things heat and cool? How many people have watched CSI at one time or another? Okay, most of us. How do they determine how long it's been since a person died?
Your body heat.
Okay, not heat, but temperature. Right, body heat would be, we take their temperature and multiply by the volume of their body. And actually, there is some of that. But basically, they do the liver temperature. So, they take a meat thermometer, jab it into the liver, and measure the temperature there.
What causes an addict to be unstable or radioactive?
Hush, Siri. Okay, so why are they doing that? Because as long as you're alive, your body's going to maintain a temperature somewhere around 98.6 degrees Fahrenheit. But when you die, your body stops producing that energy. You start cooling down toward room temperature. Or if you happen to be unlucky enough to die in Death Valley, warm up to the ambient temperature. And so you have to know what the temperature of the room was and the temperature of the body when they died, and then you use Newton's law of cooling to calculate how much the temperature would change every hour. And by looking at the temperature there and doing the how much it's changed and the rate it should be cooling from Newton's law of cooling, they determine how long since the person died. So Newton's law of cooling says that the rate at which it cools is proportional to the temperature difference between the two things. So if you throw a person, okay, let's not talk about a person. You throw a brick that is at 100 degrees Celsius, you took it out of boiling water and you throw it out in the ice, the temperature difference is about 100 degrees Celsius. Later on, when it's down to 50 degrees Celsius, is it still cooling at the same rate? No. It's cut to only half of that because the difference in temperature is only half as much. So the cooling is much faster when there's a bigger temperature difference, slower when there's a smaller temperature difference. And what direction does the heat always flow? From hot to cold. Now the greenhouse effect, and I am not going to get to electricity today, for sure. Greenhouse. How many people have a greenhouse at home? Excellent. When I was a kid, we had a greenhouse because mom and dad were all into that kind of stuff. I don't have one. When my parents built a greenhouse, of course, I thought it was kind of silly because we lived there at Monterey Bay Academy where, the coldest it ever gets is like 40. It's usually 65 to 75 every day out of the year. But Dad built a greenhouse. And I was surprised when it's bitterly cold outside, which, you have to remember, I came from Africa, so it was like bitterly cold to me when it was 60 as a child. But when it was bitterly cold outside, you go in that greenhouse, and it'd be like 80 in there. And I was like, ooh, this is some kind of magic. Now I know my dad built this thing. Well, what's going on is it's all about the radiation. Things that are hot radiate energy at a much higher rate than things that are cold. And if it's hot, we saw from yesterday's class that the frequency that it radiates is proportional to the temperature. So if it's hot, it radiates at a higher frequency. So something that's really hot like the sun is around 6,000 kelvins. The sun gives off its peak radiation in green. The sun does not look green because it's also giving off blue and red. And when we add all those colors together, our eyes see it as white. But the sun is giving off its peak radiation in green. Visible light, and that radiation goes through glass That's why I can look out the window and I can see, I think that's Mrs. Turk out there. I don't know, I can't tell. Whoo, don't want to be, no, it's not. Wouldn't want to be here anyway, that had to be cold. So sunlight can go through glass, can go through plastic. It hits the earth absorbs it, and it warms it up. But the Earth's temperature isn't anywhere close to 6,000 kelvins. The Earth's temperature is more like 300 kelvins. So the Earth is going to radiate energy with a peak frequency that's like, 1/20th or so, the peak frequency coming from the sun. That puts it in a range that we can't even see. We call it infrared, it's below red. And so the radiation coming out of the Earth is a much lower frequency. And that color can't go through the window. I said color, but it's not really color because we can't see it. But that radiation can't go through the window. So the window acts as a one-way gate. It allows radiation in at visible frequencies, does not allow radiation out at the frequencies produced by the Earth. So what's happening to the total energy if heat flows in but heat doesn't flow out? It's increasing. And so that's why it gets warmer inside the greenhouse. And so it makes it so you can have a nice, warm, growing environment when it's chilly, cold, and icy outside. Or on Earth, we also have a greenhouse effect. We have the solar waves come in and go through the atmosphere. The Earth's atmosphere is transparent to visible light and radio waves, but it's not transparent to any other waves. So the radiation that the Earth gives off, the infrared, the Earth's atmosphere is kind of absorbing and lets a little out. And so energy gets trapped in here, and that's really important. Without it, we would be icicles. We have to have the greenhouse effect locking in heat so the Earth doesn't cool. But the problem is, what if you lock in too much heat? Then the Earth gets too warm. And so we have gases in the atmosphere that will block the Earth's radiation from getting out, and we call those greenhouse gases. And if we have more of those, it's going to block energy from leaving, so the net budget of the Earth is going to be, we're gaining energy, getting hotter. Now, a clicker question, which once again, I fixed it nicely on what I have on the computer, as luck would have it. So this one here, the one you can't read, is water vapor. Can you read that? I'll just change to a letter color. I never worry about the alignment of these because you're not supposed to see them. Oh, wait, no, that's not water vapor. Water vapor was D. F is fluorocarbons. Dichloro-difluoromethane is what I have here. Now, obviously, I haven't taught about this. I'm asking you a question to see what you already know. And we still have Jocelyn, Carmen, and Candace. Okay. So we had 9 people, change to a color we can read. 9 people that said carbon dioxide, 0 that said carbon monoxide, 2 that said methane, 5 that said water vapor, and none for the last 2. All right. 9 people said carbon dioxide. Why did you choose carbon dioxide? Nine of you, that's more than half.
Plants give off carbon dioxide, and all of that's being reflected back.
Now, actually, plants love carbon dioxide. It's a nutrient to them. They absorb it.
That's what I meant.
Okay. Tiffany.
I've always heard that like singing to your plants is helpful. And I know that we weed out harsh.
Wait,
That actually is true. That now, that singing is beneficial to your plants. There have been people who've done research on that. I don't know the net results on. They don't sing. They play music from speaking system. They say, if you play rock and roll, they die. If you play Brahms, they grow. Whatever. Most people. Go ahead, Larissa.
My answer's not good. I was gonna say like carbon footprint, greenhouse effect. That's what
I was looking for.
Oh, okay.
Because all we hear about is, our carbon footprint. How much carbon dioxide are we putting in the atmosphere to contribute to global warming? But here's the harsh truth. The primary greenhouse gas is water vapor. That is the one that is the most active. There are some people that believe that the greenhouse effect is dominated by the water vapor to the point that it doesn't matter how much of some of these lesser gases we're putting into the atmosphere because it's saturated by the water vapor. Water vapor we can't control. What controls the water vapor in the air? The temperature. After that, we have things like methane. Methane is a very significant greenhouse gas. What produces, first of all, what produces water? It comes from water that's been heated up. What produces methane?
Stuff decomposing.
Yeah, stuff decomposing. A primary source of methane is cattle. My alma mater, Washington State University, did the seminal research measuring exactly how much methane is produced in both flatulence and belching from cattle. But if you believe that the Earth is going to heck in a handbasket because of man's contribution to global warming with, gases like these, the biggest thing you can do is become a vegetarian.
Vegan.
Okay, Raquel's got a full. Become a vegetarian. Don't eat cattle because they are a huge portion of the greenhouse gases. Not carbon dioxide, it's methane. Why do we talk about carbon dioxide and carbon footprint? Because since the Industrial Revolution, when we have started burning things that are produced by combustion, that level has more than doubled in the atmosphere. So we're definitely having an effect on it. And it's one that that's primarily it. Because we can take control of it and we're responsible for it. So even though it's a minor part of the greenhouse effect, it's the part that we directly can control. Except for one last caveat. They use carbon dioxide levels in the atmosphere to actually determine paleo temperatures. Because when it's hotter, the carbon dioxide in the atmosphere naturally rises. Okay, we're 3 minutes over. Sorry, you had a question, but you can walk out.
Not really about, does oxygen ever get